There are factors that affect the acidity of the acid. We can depend on these factors to rank the acids. Not always we can use the pKa table because sometimes there are molecules in there that don't have any pKa values. And this is why you would need a set of rules in order to rank different acids. The first one is whenever you have an acidic hydrogen bonded to atoms that belong to the same period. So if you have a question like that and you want to rank the acids, the first thing that you need to do is change those acids into their Lewis structure and highlight the acid that is connected to the electronegative element in there. So here I have a hydrogen connected to a fluorine, to an oxygen, to a nitrogen, and to a carbon. Then after you do this, go ahead and change the acid into its conjugate base. All what you need to do is just lose a hydrogen in there. And then check the stability of the conjugate base. Rule says that the most stable the conjugate base, the most acidic is the hydrogen. Now, how can I check the stability? The stability is based on the charge. And whenever you have a negative charge, the negative charge is bared more whenever it's present on an electronegative element. So this negative charge is going to stabilize the fluorine because the fluorine is the most electronegative element among all of those. Carbon is not an electronegative element. So when a negative charge is on a carbon, this is going to destabilize the carbon. So it's going to make the conjugate base less stable and it's going to make its acid less acidic. So what you're looking for is a conjugate base that bears the negative charge. To bear the negative charge, it needs to be very electronegative because electronegative elements normally they can hold the negative charge better than non-electronegative elements like carbon, for example. So that is going to make the conjugate base stable, and the more stable the conjugate base, the more acidic is the acid. So this is why HF is the strongest acid among all of those. Now, let's say, for example, if your acid is connected to elements that belong to the same group now. As we discussed before, now you don't look at the electronegativity anymore. You have to look at the size of the ion. And we said that we need to check the ion because it's the ion that is the conjugate base, and it's the ion that bears the negative charge. So the bigger is the ion, the more surface area the negative charge is distributed upon. This is going to make the conjugate base more stable and it's going to make the acid a stronger acid. So whenever your acidic hydrogen is directly connected to elements that belong to the same group, then in this case you have to apply the size of the ion rule rather than the electronegativity in there and go with the size. The bigger is the ion, the more distributed the charge is, the more stable is the ion, the more acidic is the acid. Let's have an example in there. If you have water and H2S, and I ask you which one is more stable, well, you have to change each one of those first into its Lewis structure. After you do this, go ahead and change each acid into the conjugate base. Before, you have to highlight, of course, the hydrogen that you are looking for, because after all, it's this hydrogen that is going to be acidic, either one of those, right? So you have to look at the element that is directly connected to the hydrogen. This is oxygen versus sulfur. So now I am looking at elements that belong to the same group. I know that sulfur and oxygen both belong to group number 6. As I go down the group, sulfur is a bigger ion than oxygen. So the negative charge will have a higher surface area distribution. This is going to stabilize the ion. It's going to make the acid more stable. If we have another example and we are comparing the acidity of the following two compounds, so if we have a CH3O, CH3, this is called an ether compound. We will study all of these functional groups, versus if I have a sulfur CH3 and a CH3. And I ask you which one of these is more acidic. So first of all, you need to highlight the acidic hydrogen. I know over here that this is symmetrical, so these hydrogens in there are the ones that I am looking for. So let's go ahead and draw the Lewis structure for each one of those and pick a hydrogen. If you notice for both structures, the hydrogen is connected to the carbon. So I'm just going to pick one hydrogen off these three hydrogens in there. These three hydrogens are similar to these three hydrogens, so I'm just going to highlight one hydrogen in there. Okay, and then for the other structure, it's going to be the same thing. Here you go. I'm just going to also highlight one structure. I just want you to see the difference between this example and the example before. The hydrogen, the acidic hydrogen that I have here, is connected in both examples, not to the sulfur, not directly to the sulfur or oxygen. It is connected to the carbon. So here, both of these hydrogens, they are connected to the same element. If this is the case, then you cannot look at the group anymore. We looked at the group in the example before because the hydrogen was directly connected to the oxygen and the sulfur. So we could easily compare by the group size. But because the hydrogen that I want to target and I want to classify is connected to the same element here now, then I need to look at electronegativity effect on this hydrogen. Which one is more electronegative now, the oxygen or the sulfur? Of course, the oxygen because it's more electronegative. So the oxygen is going to pull electrons away from the carbon, right? Now, when it pulls electrons away from the carbon, it's as if it's pulling electrons away from the hydrogen as well. So that is going to make this hydrogen more partial positive than the sulfur. You could have changed this into a conjugate base. So you have your C, hydrogen, hydrogen. You could have changed each one of those into the conjugate base in there. And you can easily see if you change into a conjugate base, then you would see there that the negative charge is going to be, here you go. So the negative charge on both is on carbon in there. But the pull of electrons is going to be more towards the oxygen rather than the sulfur. So that is going to stabilize this ion more, and it's going to make this hydrogen to be more acidic. Let's have another example. If I have these three compounds, ammonia, HF, and water, let's rank them in increasing acidity. So we're going to change each one of those into their Lewis structure and highlight the hydrogen that we are interested in. This is going to be the acidic hydrogen in there. And then change each into their conjugate base. So this is the hydrogen. I have a hydrogen connected to the nitrogen, hydrogen connected to fluorine, and hydrogen connected to the oxygen. The nitrogen, oxygen, and the fluorine, they belong to the same period. This means that I have to look at the electronegativity in there of the conjugate base. And the one which is more electronegative, so this is the conjugate base. The conjugate base here is F minus. F minus is more electronegative than OH negative, than the O negative there. So it bears the negative charge more. This is a more stable conjugate base. This is gonna make the acid more acidic in there. And then you have your nitrogen. Nitrogen is going to be the least stable conjugate base because this guy is going to be the least electronegative, less acidic. So if I want to go ahead and drag those from as increasing acidity, meaning from the least acidic to the most acidic, NH3 is going to be the least acidic, then I'm going to end up having water, and the most acidic is going to be the HF. Just take it as a rule that nitrogen behaves more as a base than as an acid whenever it is in a neutral form. So whenever you see a nitrogen with lone pairs. Then in this case, the nitrogen is going to behave as a base. So if I am comparing a nitrogen with a lone pair versus an oxygen with a lone pair, and I have the hydrogen directly connected to each one of these elements there, this is a lone pair over here. So in this case, definitely the hydrogen that is connected to the oxygen, because oxygen is more electronegative, it's going to be more acidic than that hydrogen connected to the nitrogen. Let's have another example. Ranking also and increasing acidity. You have OH minus, you have H3O plus, and you have water. Whenever the charges are there, you don't have to change into a conjugate base because it's pretty much obvious. Let's write the Lewis structure for each one of those. Here you go. I have a negative charge. I don't have an acidic hydrogen here. I have an O with a negative charge. This hydrogen is not acidic. It's not acidic. I cannot take a hydrogen and leave the structure with just an oxygen there. And then you have your hydronium ion. Here you go, with a plus charge. And then I have water. So here I have different charges. I have a neutral. So I have a hydrogen connected to an oxygen. This is going to be my acidic hydrogen here. I have here an hydrogen connected to an oxygen with a plus charge. Here the oxygen is a neutral form. Here an oxygen with a plus charge. And here I have a hydrogen connected to a negative oxygen. So if I want to compare between those three, the rule says that negative charge is a sign of basicity. So immediately I would say that the OH minus, this is basic. It's a base from the oxygen. It's base from the oxygen. So the hydrogen next to the oxygen is not acidic at all. Every time you see a negative charge, this guy is going to be a base. It's not going to be an acid at all. To compare between positive oxygen and the neutral oxygen, a positive charge on the oxygen, this is called a cationic oxygen. A positive charge on the oxygen will increase the acidity of this hydrogen. So whenever you see a plus charge on the oxygen, this is more acidic than a neutral oxygen. So this is going to be the most acidic, H3O plus. So that is going to be your most acidic in there. And then water is going to be in between. So if I want to rank in increasing acidity, I'm going to start with the least acidic, which is the OH minus. It's going to be the least acidic because of the negative charge. The H3O plus, the positive charge, is the sign of acidity every single time. So negative charge is a sign of basicity, positive charge is a sign of acidity, and then you have the neutral compound in between. Let's have another example and arrange these compounds in a decreasing acidity. Decreasing acidity, this means that I want to start my rank from the most acidic to the least acidic. Okay, now whenever I see that I am comparing between charges, positive charges, and the neutral compounds, I don't need to change into a conjugate base, you guys, because cations are always more acidic than neutral compounds. And because oxygen is more electronegative than nitrogen, then in this case, um, the oxygen cation is going to be more acidic than that of the nitrogen cation. Likewise, if I'm looking at the neutral compounds have what? Have a nitrogen and an oxygen. Okay, because what I am looking here is for the acidic hydrogen. So this is the acidic hydrogen that I want to compare versus this acidic hydrogen. Always your acidic hydrogen needs to be connected to the electronegative element. So this is why for this structure, I chose this acidic hydrogen to rank and not this hydrogen that is connected to the carbon. because carbon is less electronegative than oxygen. So definitely this hydrogen is going to be way more acidic than this hydrogen there. And then this hydrogen over here. And you can see over here that the neutral compound containing the oxygen is more acidic than the one containing the nitrogen. Why? Because oxygen is more electronegative than nitrogen. So if it's more electronegative than nitrogen, it's going to pull the electrons away from the hydrogen, and it's going to make the hydrogen more partial positive. The more partial positive the hydrogen is, the more acidic it is. So to rank, in this case, the most acidic one will be, I'm just going to go ahead and number those. So the most acidic one will be the oxygen with a plus charge. And then after this, you will have the nitrogen with the plus charge. So you rank your positive charges first because a positive charge is a sign of acidity. After that, you go to the neutral compounds because nitrogen and oxygen, they both belong to the same period. Then I need to look at the electronegativity. The one which is more electronegative is the one which is the most acidic. So this one is going to be the third, and the least acidic is going to be the hydrogen that is connected to the nitrogen. Inductive effect is another factor that we use to determine the acidity of acidic hydrogens. By definition, an inductive effect is the pull of electrons through the sigma bond, and it is caused whenever you have an electronegative element that is very close to the acidic hydrogen. The closer the electronegative element is to the acidic hydrogen, the more stable is the conjugate base and the more acidic is the acid. Also, the more electronegative elements you have closer to the hydrogen, the more or the more stable the conjugate base is, and the more acidic is the acid. Here I have two examples, and both of these examples have an OH function group. This is an alcohol function group. Now, this hydrogen over here is connected to the oxygen in both of these examples. But there is a difference between the groups that are attached to the carbon chain. In this example, I don't have any electronegative elements. So when I change this into its conjugate base, then the negative charge on the oxygen will be localized, meaning that it will be fixed on the oxygen. Nothing is going to move it because oxygen is more electronegative than the sp3 hybrid carbon. So the negative charge and the electron cloud will remain on the oxygen. It will not be distributed. That will destabilize the conjugate base and make this acidic hydrogen less acidic compared to the other structure. For the other structure, you have your electronegative elements on one of these carbons in there. Now, these electronegative elements, because they are close to the acidic hydrogen, if you change into a conjugate base, notice that the flow of electrons. The flow of electrons is going to be towards the fluorine. And notice how the pull is towards the fluorine through the sigma bond. This is the definition of inductive effect. Now, all of these electronegative elements that you see over here, these, because of the difference in electronegativity between the fluorine and the carbon, we call them electron withdrawing groups. These electron withdrawing groups, they withdraw electrons. They steal electrons away from the carbon, from this adjacent carbon, and from the electronegative oxygen. So the electronic cloud for this conjugate base is going to have the electrons being distributed over the oxygen and the carbons and the fluorine. They are not going to be concentrated on the oxygen. So that is going to stabilize the conjugate base. Every time we talk about conjugate base stabilization, we always link this to the charge. The more distributed the charge over the surface area of the molecule or the ion, the more stable is the conjugate base. And this is going to make the acidic hydrogen more acidic. Let's have another example. This other example has an acid functional group. This is called a carboxylic acid functional group. You don't have to worry about the naming now because we will talk about the naming as we proceed in chapter 3. So this is the carboxylic acid functional group. And the acidic hydrogen is this hydrogen because it is connected to the oxygen. And I have three structures here. And all of these structures, they are made up of the same number of carbons in there. So I have 4 carbons in each one of them. Now, my question here, which one of these acids, or rank the acids in increasing acidity? So from the least acidic to the most acidic. So what you need to do over here is to change every acid into its conjugate base. Now we know that all of these acids, of course, they have the acidic hydrogen. Let's go ahead and highlight the acidic hydrogen. So this is my acidic hydrogen here. This is my acidic hydrogen here. This is my acidic hydrogen here. Notice that all the acidic hydrogens are connected to the same element, which is the oxygen. So this is why I need the conjugate base now for me to check its stability and relate that to the acid strength. So I have my chlorine over here and the negative charge. Don't forget this. So let's go ahead and do this for every single one of them. Now, these conjugate bases, we need the charge not to be localized on the oxygen, but we need it to be distributed over the most surface area possible in there. However, the distance or how close the electronegative is to the O negative, that is going to be a concern because notice here the chlorine, how far away it is from the electronegative element. So if it is far away from the electronegative element, it's not going to pull the electrons. It's pulling effect or it's electron withdrawing effect. So you have an electron withdrawing effect for this chlorine, but the electron withdrawing effect is going to be very low because the chlorine is very far away from the oxygen. The closer the chlorine is, the stronger the pull, stronger the inductive effect or the pull through the sigma bonds. So between those two, I can easily say that this one is going to be the least stable conjugate base. So it's going to be the least acidic. So this hydrogen is going to be the least acidic. Now, as the chlorine goes closer to the acidic hydrogen, so in this case over here, see how chlorine is very close to the acidic hydrogen. It's actually adjacent to it. So the acidic hydrogen is connected to the oxygen, to the carbonyl, and then immediately you have the chlorine in there. So the chlorine is going to have an electron withdrawing effect more in this case, and the electron pull is going to be towards the chlorine, as you can see. So the charge here is going to be distributed not just on the oxygen, it's going to be distributed over this whole surface area, making this conjugate base more stable, making this acid to be the strongest acid. So if I want to arrange those in increasing acidity, then definitely this one is going to be the least acidic, and this one is going to be the most acidic. Let's have another example. Okay, now in this example, I'm still having a carboxylic acid. So let's highlight our acidic hydrogen. So all of these hydrogens, they are connected to the oxygen. So now I'm going to go ahead and look at the inductive effect. So again, change each one of those into the conjugate base and check the stability of the conjugate base. This is a negative charge. This is a chlorine in there. Let's write the chlorine in a better way. So you have your chlorine. And then now notice here I have the amount of the chlorine. This is the difference. The chlorines are close, but the more chlorines I have closer to the O negative, the more stable is the conjugate base because the effect of the electron withdrawing group now of the chlorine is going to be more because I have, in this example, I have 3 different chlorines or 3 chlorines. versus here I have two chlorines that are closer to the O negative versus I have one chlorine that is closer to the electronegative element versus here I have no chlorines whatsoever. So since I have no halogens in there, no electron withdrawing group, that is going to destabilize the conjugate base. So this conjugate base is not going to be stable because the negative charge here now is only doing resonance. So it's only moving in this area between those two oxygens there. You have resonance. Remember here you have resonance. So the negative charge is distributed only between those two oxygens. That is compared to the others. This is going to be the least stable conjugate base. So this acid is going to be the least acidic. So as I increase now the number of chlorines in there, the effect of the electron withdrawing group is going to get higher and higher. So I am expecting that this conjugate base over here to have a stronger inductive effect, and it's going to be more stable. So its acid is going to be the strongest. So this is why this guy is going to be the most acidic. Another example. In this example here, I'm comparing the acidity of the carboxylic acid, of different carboxylic acids in there. Now notice that all of these carboxylic acids, they are bonded to the same atom, which is the oxygen. So in this case, I need to apply the electronegativity rule and not the rule for the atoms that belong to the same group. So notice here, I have a fluorine, I have a chlorine, I have a bromine, I have iodine, and I have no halogen on this carbon. Because the halogen is not directly connected to the hydrogen, I can no longer compare the acidic hydrogen based on the group effect. I have to compare the acidic hydrogen based on the electronegativity and how powerful the electronegative atom is. So I have here different types of electronegative elements. I have a fluorine, I have a chlorine, I have a bromine, and I have iodine, and I have no electronegative element on this structure here. So as you can see, the fluorine here is very close to the acidic hydrogen. So if I change this into a conjugate base, then I'm going to end up having my CH2, my fluorine, my carbonyl, and then I'm going to have the O negative in there. Now, the F there is going to be the strongest electronegative element compared to all the other halogens. So it's going to have the most inductive effect. So it's going to pull electrons more because it's more powerful. It's going to pull electrons more from the oxygen, distributing the charge over a larger surface area, and they're compared to the chlorine, to the bromine, and to the iodine. So this is going to make the conjugate base more stable, and it's going to make this acid to be a stronger acid. So if I want to rank the acidity in a decreasing order, then definitely the fluorine, the acid which is close to the fluorine, is going to be more acidic than that of the chlorine, than that of the bromine, than that of the iodine. And the one that has no electronegative element on the carbon, this one is going to be the least acidic. The third factor that affects the acidity is the resonance. And it's the same idea because what you're doing here is you are working with the conjugate base every single time. And you are checking the stability of the conjugate base. So you need the charge on the conjugate base to be delocalized, meaning that to be covered over a larger surface area. Let's have these two examples. I'm comparing an alcohol versus a carboxylic acid. Both have hydrogens in there, and both of these hydrogens is connected to the oxygen, which is the same electronegative element. So you have to change each one of those into the conjugate base and see how stable is the conjugate base. The stability of the conjugate base is based on the charge distribution. Here, the negative charge is localized on the oxygen. It's not going anywhere. It's not distributed over the carbons, it's just on the oxygen. Here, the negative charge is distributed between the two oxygens, so it's a higher surface area. Take a look at its resonance and the hybrid. So since it is delocalized over a larger surface area, then in this case, this is going to be a more stable conjugate base, then its acid will be stronger. By definition, always carboxylic acids are way more acidic, or the hydrogen of the carboxylic acid is way more acidic than that of the alcohol. So let's have another example. If we have two compounds asking which one is more acidic, first thing that you need to look for is the acidic hydrogen. These three hydrogens are the same as these three hydrogens. So simply go ahead and draw the conjugate base and take out just one hydrogen from these three. I'm just going to choose this end in there. And the conjugate base now is going to be a negative charge, a carbonyl, and the CH3. So lose a hydrogen and get the conjugate base. Okay, now the conjugate base of this one, we have different types of acidic hydrogens. These two hydrogens are acidic and these three hydrogens are acidic as well because they are close to the carbonyl. The reason why we said that these hydrogens are acidic because they are close to the carbonyl, close to the oxygen. Oxygen takes electrons away from the hydrogen and make it partial positive. But just think about it like that. The closer or the more carbonyls you have around the hydrogen, the more acidic is the hydrogen. So if I'm comparing those hydrogens here that are closer to one carbonyl versus these two hydrogens that are closer to these two carbonyls, these two hydrogens are going to be way more acidic. So if I have a base, the base is going to come and take one of these hydrogens in there. Not the hydrogens of the CH3s, it's going to take the hydrogens of the CH2s, one of the hydrogens of the CH2s. So the conjugate base is going to look like that. It's carbonyl, it's a CH, not a CH2, it's just a CH with a negative charge, and then a carbonyl and a CH3. And this is the conjugate base. Now the question is, which one of these conjugate bases is more stable? To determine the stability, look for resonance, and we need the distribution, the charge distribution to be distributed over a larger surface area. And remember the conditions for resonance. The more the negative charge is localized on the oxygens, because oxygen bear more the negative charge than carbon, then the more acidic is the acid. So here, if I am doing my resonance structure, so if you want to do the resonance structure in here, you start with the lone pairs, move it towards the single bond. The double bond is going to form a negative charge. So my resonance structure here is going to have a double bond and O negative. So notice here that the negative charge is moved between the carbon and the oxygen. Which one is a major resonance contributor between both of these? It's definitely this one because the electronegative element normally is better dealing with a negative charge than the carbon dealing with a negative charge. So this is going to be a major resonance contributor in there. However, the charge distribution is in this area. It's between the carbon and the oxygen. On the other hand, if I want to draw the resonance structure here, I do have two resonance structures because the lone pairs can move this way, giving the oxygen a negative charge. So I'm going to end up having my first resonance structure here with the negative charge on the oxygen rather than the carbon. This is a double bond. This is a carbon double bond O and the CH3. Okay, or I can have a second resonance structure where the negative charge is going to, where the negative charge is going to delocalize on the other oxygen. So my second resonance structure will be this guy over here. This is a double bond O. This is a CH, a double bond, a carbon. Now your negative charge is on this oxygen and the CH3. So notice that your negative charge is divided between two electronegative elements versus one electronegative element in there. So that is going to make this structure more stable because the charge is more localized over a higher surface area. And the negative charge is not just on the carbon, it is on the oxygens as well. And for this, if your conjugate base is stable, then the hydrogen is going to be way more acidic. This is why if I am comparing between a hydrogen that is connected between two carbonyls and the hydrogen that is next to one carbonyl, the hydrogen that is between two carbonyls is going to be the most acidic. Let's have another example. We have three different molecules. Which one is more acidic? You need to locate your acidic hydrogen and to change each one of them into a conjugate base by taking away the acidic hydrogen. And then checking the charge and how it is delocalized, in this case by resonance if there is any resonance. So once you change into a conjugate base, you can easily see that the charge is focused, localized on the oxygen. There is no resonance in there. Here, the charge is going to be on the oxygen, and there will be two resonance structures. And the negative charge will be distributed between the two oxygens. It's on this oxygen and it's on the other one. And in the last one, you will have a negative charge on the carbon. This is the conjugate base, and the negative charge is going to be distributed between the carbon and the oxygen. We know that carbons, they don't bear the negative charge. So the moment you see a structure that has a negative charge on the carbon compared to a structure that has a negative charge on the oxygen, even though there is no resonance structures for this one, but the oxygen bears the negative charge more. This means that it stabilizes the conjugate base more. So if I am to compare between the conjugate base of acetone versus the conjugate base of methanol, definitely the conjugate base of methanol is going to be more stable, then it's going to be more acidic than that of the acetone. The strongest acid is the acetic acid because it is a carboxylic acid and the negative charge is distributed between the two oxygens in there. So that is more stable because of resonance. This is going to be the strongest acid. After that, we have methanol, it's going to be the second strongest, and then the least or the weakest acid among all is going to be the acetone. And the primary reason is because not because there is resonance, because we know that this guy has resonance, this one has no resonance. It's because the negative charge being on the less electronegative element, which is the carbon. Another factor that determines the acidity of the acid is hybridization. Normally, we use this whenever the acidic hydrogen is connected to either a triple bond, a double bond, or a single bond, meaning that we're working with hydrocarbons. When an acidic hydrogen is connected to an sp hybrid carbon, that is going to be way more acidic. This means that the chances of a base coming and taking this hydrogen is way more than the chances of a base coming and taking the sp2 hybrid carbon, than that taking then the base taking the hydrogen connected to the sp3 hybrid carbon. So in order to determine the different types of acidity, all what you need to do is just change into a conjugate base as we used to do and check which conjugate base is more stable. The stability of the conjugate base here lies on how close the lone pairs are to the nucleus. And the closeness of these lone pairs depends on the s character of the orbitals. So the more s character or the more percentage of s orbitals you have, the more stable is your conjugate base. This is the anion. The more stable is the ion or the anion, and the more acidic is the acid. The sp hybrid orbital is a 50% s character because the s constitutes half the total number of orbitals. Here the s constitutes one third, so it's going to be a 33 s character, and here it's going to be a 25. So as you increase the percent of s character, the ion is going to be more stable because these lone pairs are going to be pushed more towards the nucleus, decreasing the length of the bond. So this bond is going to be a shorter bond compared to the bond that is connected between the sp3 hybrid carbon and the hydrogen. And that is going to make the conjugate base more stable, and it's going to make its acid way stronger. Let's have a couple of examples. So let's say if we have an alkane, okay, and we are working with a base. So the base is sodium amide. Put your charges, please, so that you can know that the nitrogen here, there is two more lone pairs. Let's go ahead and add these two more lone pairs, okay, for the amide. Now this base is going to come and take the acidic hydrogen, but because all the hydrogens that are connected to an sp3 hybrid carbon, then in this case, none of these hydrogens are going to be an acidic hydrogen. So there will be no reaction. If you have a triple bond, then definitely you're always going to be looking at the carbon. So you have two carbons over here. At the sp hybrid carbon, we have two sp hybrid carbons in there. Okay, so the base is going to come and take the acidic hydrogen and it's going to add lone pairs. So you're going to end up getting your acetylide ion